This is lesson 2-4, one solution, no solutions, or infinitely many solutions, and it's going to start on page 108. This is example 1 on page 108. And it says, for what values of x will the rectangle and triangle have the same perimeter? All right, let's just review very quickly. Perimeter is the distance around something. So on my rectangle, I would add 2x plus 3, x, 2x plus 3, and x to get its perimeter. On the triangle, I'd take 2x plus 2, another 2x plus 2, and another 2x plus 2. I would add those all together. And remember, I want these to be the same. So let's start with the rectangle. I have two sides that are 2x plus 3, and I have two sides that are x. And I want to know when that is equal to my triangle. Three sides, each one is 2x plus 2. All right, let's distribute. 2 times 2x is 4x. 2 times 3 is 6. 2 times x is 2x. Let's do the triangle side. 3 times 2x is 6x. 3 times 2 is 6. All right, I clearly need to clean up on the left side. So let's put the x's together. 4x's and 2x's make 6x's and a 6 on the left. And I had 6x's and 6 on the right. Now I'm going to stop right there. I don't have to go any further because I realize that both sides are identical. And when both sides are identical, it's not going to matter what your x value is. It is always going to work out. Now, if you wanted to, you absolutely could do your next step. When we have variables on both sides, we pick on the little guy, but they're the same, so it doesn't really matter. I'm going to take 6x's off of each side, bring down, bring down. That is always a true statement, no matter what your variable is. And when that's the case, when you have identical things on each side, that means you have, are you ready for this? An infinite number of solutions, or you might say infinitely many solutions. In this lesson, it's going to be okay for you not to complete your work fully to the very end. The minute you see something like this, where you have identical expressions on both sides, you can stop and you can say there's infinitely many solutions. This is the try it on the bottom of page 108, and since it comes directly after the infinitely many solutions problem, I'm guessing I already know how many solutions there will be, but let's go ahead and work it out anyway. So here is our problem. I'm going to rewrite it. I probably am not going to use their boxes because you know me and their boxes. All right, I have 3 x's and 15 on one side. Let's clean this up a bit. 2 x's and another x is 3 x's, and wait a minute, 10 plus 5 is 15. The minute I see I have the exact same thing on both sides, I can stop. You could keep going if you want, but I'm going to stop and I'm going to say there are infinitely many solutions. I'm going to have to work on this sign. That's a sad infinity symbol. This is example number 2 on page 109. It says Anna and Lee played soccer for the same number of hours one week, and we would like to know how many hours did Lee play on Sunday. So let's figure out how your book came up with their equation, because ultimately you also will be building the equations, so it's important for you to understand the process. So they started with Anna, and if you look, every day Anna spent X hours in the morning and 1.2 hours in the afternoon. There were 1, 2, 3, 4 of those. right there. They distributed, and that's how much Anna has on the left-hand side of the equation. But Lee's a little different. He did different times every day. That's Sunday. That's Monday. That's Tuesday. And that's Friday. And they're going to add them together. They're simply going to combine their like terms. 1x and 2x makes 3x. 2.5 and 4.5 makes 7. So I want to point something out to you. This is Anna. And this is Lee. There is nothing in common. So if you remember, if we were going to have an infinite number of solutions, I would have the exact same expression on both sides, but that's not the case. I don't even have anything similar on both sides. If you have all different stuff, that's an old-fashioned equation. There's going to be one solution. And so when we solve this, we have a variable on both sides. We're going to pick on the little guy. We're going to get rid of 3 x's off of both sides. That leaves an x and a 4.8 on one side, 7.0 on the other. We're going to look on the side with the variable. We're going to subtract off 4.8. And x will be 2.2, which is exactly how much Lee played on Sunday. So every once in a while in this lesson, you will have one solution just to keep your math skills up. This is example number 3 on page 109. Jill makes 3 bracelets and Mika makes 2 bracelets. They both use the same number of string colors, and we would like to know how many colors should they use to make the same amount of money. Now this is a no solution problem, so let's see how this is going to look to us. Let's start with Jill's bracelets. Here's Jill's data, and it says $5 per bracelet plus $2 for each string color. So, because the string color is going to happen over and over and over again, the string color gets the X plus a one-time $5 fee. But you have to also remember she did 3 of those. So 2 times the string color plus 5, all multiplied by 3 bracelets. All right, let's look at Mika. Mika has $3 per bracelet plus $3 for each string color. So because the string color is happening over and over and over, it gets the X. But remember, Mika made 2 of those. So this is the string color plus the bracelet times 2. Now they went ahead and they did our distribution for us. They did 3 times 2, x is 6x. 3 times 5 is 15. They did 2 times 3x is 6x. 2 times 3 is 6. And I would stop there, because this is an interesting situation. I have exactly the same variable term. There is a 6x on the left and there's a 6x on the right. The difference is your constant. And when your expressions are similar in this way, you have the same variable term but different constants, you will have no solution. So let me show you why that works. If we were going to move on using our steps, we have a variable on both sides, so we would pick on the little guy. So we would take 6 x's off of both sides. I would bring down, I would bring down, I would bring down. There is no variable on earth that is ever going to get 15 to be the same as 6. Now I want you to be careful when you answer this one. There's a couple ways to answer this. You can say that your answer is the empty set. This is the empty set. Or there's no solution like that. Or there is no solution. I do not want you to say the solution is 0. The answer is not 0. If you put 0 into your equation, it would not work out. So don't do that. Pick one of these other options. This is the try it at the bottom of page 109. It says, how many solutions does the equation 4x plus 8 equals 0.1x plus 3 plus 3.9x have? All right, kids, let's go for it. 4x plus 8 on one side. Let's go ahead and combine some like terms. 0.1x and 3.9x makes 4x and 3 on the other. Now I would stop, because although these are similar, they both have the same variable term. Their constants are different. There's no variable that can be on this earth that is going to make that work. This is no solution, the empty set, or you can do this. If you wanted to keep working, you could. You could take 4x's off of one side, 4x's off the other. And as I said, nothing is going to make that work. Nope, no solution. We actually have an example 4 in this lesson. It is on page 110. And all it is telling you is that, you know what? Sometimes you can stop your work early and you can just use your brain and your eyes to look at what you have and make a decision. So, example number 4 says, how can you determine the number of solutions each equation has without solving? On A, I want you to look at A. Same variable term, different constants. That's never, never, never going to work out. And so this one has no solution. For B, they went ahead and they did their distribution, 3 times x, 3 times 4. When they looked, it was identical. Both sides identical means I have an infinite number of solutions. And here is C. If you look at it, each side is different. My variable terms are different. My constants are different, which means that I have to go and do the entire thing. So let's start with the step that says, if I have a variable on both sides, let's pick on the little guy. Take 2 x's off. This is 3 x's plus 8 on one side, and be very careful, that's a -1 on the other. Look on the side that has the variable, get rid of that constant. 3 x's on one side, -9 on the other. And last, we're going to divide by 3, and x will be -3. One solution. This is the try it on page 110. I want you to answer A, B, and C, and when you are all done, I want you to come back for checking. So pause me now. All right, on letter A, different variable terms, different constants. This one is going to have one solution. On B, I'm going to distribute 3 times x is 3x. 3 times 2 is 6, that's the left. On the right, I have 3x minus 6. Well, same variable term. Uh-oh. Different constants means there is no solution. And the last one, 9x is minus 4 on the left. 9x is minus 4 on the right. Those appear to be identical, which means I have an infinite number of solutions. This is your key concept on the top of page 111. All right, so here we go. You have infinitely many solutions when you have identical expressions on both sides. You have one solution when everything is different. Your variable terms are different, your constants are different. And then you are going to have no solution in the case where you have similar expressions. In this case, you're going to have the same variable expression or variable term, but different constants.